And welcome to my tech farm. My name is Igor, and Polymaker company give me very big homework because they send me all these filaments. This is the complete PolyLite line, PLA, PETG, ABS, ASA, polycarbonate, and this is the Polymax. But it will be too big to present everything in one video, so in this video I will test and compare only the PolyLite line. I repeat those now standard tests which I do on this channel, so the results will be comparable not only with each other, with these 5 filaments, but also with those which I did in previous videos or in future videos, for example with the Polymax in few weeks maybe. I already have some filaments from this range, but the Polymaker decided to send me everything new because they want me to comparable with each other as much as possible. So every filament will be new and will be open exactly before the printing, and I will not dry them, so I will use them as they are out of the box. Of course, always first we'll be printing the temperature tower, and then I will decide on which temperature I want to print those test specimens. And when all test objects are printed, I will start with mechanical testing. I'm very happy actually when I will test different types but from same brand, because in this case we can learn more about the different types and properties about these materials. Just very shortly and quickly. PLA, actually quite strong material, but two problems I have with it. One is it's a little bit brittle, but the biggest problem is that its heat deflection temperature is around 50-55 degrees Celsius. This means if you left your PLA part in your car on hot summer day, they will deform. PETG is a little bit better from this aspect. Heat deflection temperature is around 70, maybe 75 degrees Celsius, and it doesn't need an enclosure. For PETG you have to pay attention that it must be dry, but not so sensitive like nylon, so you can take it out from the box, print it, and then immediately put it in some vacuum bag or something where you place a silica gel inside. ABS, heat deflection temperature should be around 90 degrees Celsius, actually similar to ASA. Usually injection molded plastic parts in a cart are made from ABS. But it requires an enclosure because it can warp sometimes from the bed surface, and even the layers can detach. I think it's called crack or something like that. So it's recommended to print inside an enclosure, and it may have some other smell during the printing, so it's good if you have some exhaust so you can take out the air from that enclosure when you finish the printing. ASA is very similar to ABS. It's a little bit expensive material. Biggest difference is that it is UV resistant. So if you want to print something which will be constantly outside on the direct effect of the sun, in that case ASA would be a better choice. And polycarbonate, it also needs printing inside an enclosure. It should be printed, I think it's on a little bit higher temperatures, and but it has bigger thermal resistance, and we will see about its mechanical properties. Okay, let's start with the PLA. PLA sticker and user manual. And we have the spool in this vacuum packaging, and what is important that it is resealable. And the Polymaker know that how important it is to keep the filaments dry, so if you cut it along this line, you can place back the silica gel and close it the back after the printing is finished. Very nice transparent spool, and here we have holes to lock the end of the filament, and there is a sticker, and I'm not sure how accurate it is, but there is some kind of ruler. We can see the scale, how much filament we have on the spool, here in meters and here in grams. As size, the recommended printing temperature is from 190 and 230 degrees Celsius. I will print the temperature exactly in this range, but starting from the highest temperature. The adhesion is good, so I will wait until the print surface cools down. Analyzing the temperature tower, I cannot see any difference between the bridging or the stringing on any temperature. And of course, with overhangs there is some difference, but even on highest temperature it is quite acceptable. Only here on 60 degrees it has some problems, but these three are perfect. So all test specimens I print on 210 degrees Celsius. Later we compare all temperature towers with each other before I start with the mechanical testing. The next material is PETG. Now it arrives on this cardboard spool, and what you should know about PETG that it is sensitive to moisture, but I will not dry it, I will print as it is now out of the box. And since the recommended printing temperature is between 230 and 240 degrees Celsius, the temperature tower will have only two elements. For the bed I will use 80 degrees Celsius, and for part cooling it's recommended to disable the fan, but I will left it to 15%. There is a hole, we can see how many filaments we have on the spool, and there is a scale in grams. But for the first look it looks okay, the bridging is great and absolutely no stringing, so this means the filament is dry. Only problem I can see with this overhang, and the reason for this is the weak part cooling. 15%, well, it's even more than suggested, because they said no cooling at all. So the test specimens will be printed at 235 degrees Celsius. The next material is ABS, it is in green color. And it also arrives in this vacuum packaging, which is resealable, only I have to cut it here. And again, we have some basic information about the printing here. The printing temperature is between 245 and 265, so this temperature tower will have three elements. And here we can see how on the scale how much filament we have on the spool. And the ABS will be printed inside this enclosure, and I will use some glue stick on the print surface for the better adhesion. Closing the enclosure, and I will follow the temperature inside with this thermometer. The sensor is approximately here behind the spool. 265 to 245. Now it is printing the second element on 255 degrees Celsius. And the printing is finished. The temperature inside the enclosure went up to 46 degrees Celsius. There is no that unpleasant smell of the ABS. Immediately I want to check the bed adhesion, which is great, and I know this combination of Wham Bam packs plus the glue stick works great with every ABS and ASA. And quality of this printing is really great. The bridging is perfect, the stringing is never the problem with the ABS, and look at this overhang. On 265 it had some problems, but on 255 it was much better, and almost perfect on 245. But of course I will print out the specimens in the middle, and if everything will be okay with the layer adhesion, this ABS might easily become my new favorite ABS filament. And now starting with printing of test specimens on 255 degrees Celsius. The bed already cooled down and I even heard some cracks because it's shrinking, and probably it will be very easy to remove the parts. Yes. And the next one is ASA. It is in this some kind of red or brown color. And this bag is also resealable. The printed temperature between 240 and 260 degrees Celsius. So this temperature tower will have 3 elements. ASA temperature tower starting from 260 degrees Celsius. This is the printing of the second element now. Printing is finished. Quick check of the bed adhesion, which is great as usual. I wait until it cools down and then analyze the temperature tower. This temperature tower is very similar to ABS version. The bridging is great, absolutely no stringing, and the overhangs, this is the worst, but these two are quite acceptable. The bed is already cooled down to 40 degrees Celsius. And the last filament in this video is polycarbonate. And this bag is also resealable. Polycarbonate is in this nice transparent color, and the printing temperature is between 250 and 270 degrees Celsius. So this temperature tower will have 3 elements. Bed I will heat up to 100 degrees Celsius. Everything looks fine so far. There is no sign of the warping. And it's still printing the first element on 270 degrees Celsius. And the temperature inside the enclosure is 41 degrees Celsius so far, but it will go up to 45. This is the second element. The temperature inside the enclosure is 45 degrees Celsius constantly. And the printing is finished. Quick check of the bed adhesion, which looks like it's great, absolutely no sign of the warping. And for the first look, this looks great, but I have to wait until it's cooled down to take it off. And this is almost perfect temperature tower on every temperature. The bridging came out perfectly, very minimal stringing, but hardly noticeable on 270 degrees Celsius. But look at this overhang. I hope it's visible on camera too. Perfect overhang even on 60 degrees on highest 270 degrees Celsius. And absolutely no sign of warping. So all test specimens I will print on 260 degrees Celsius. So far so good, and it's a perfect first layer. It's hard to see from this angle, but looks like every object is perfectly straight, there is no warping. And the printing is finished. Now the bed temperature cools down to 30 degrees Celsius. So let's see, it's very easy to remove these objects. And now let's compare the temperature towers. PLA, PETG, ABS, ASA, polycarbonate. PLA, PETG, ABS, ASA very similar, and far the best polycarbonate. The tensile strength test. These test specimens are printed in horizontal position. The smallest cross-section area is 4 by 4 millimeters. All objects broke on that smaller cross-section area. An interesting property I noticed with ABS that always before it breaks become white, and this property may be useful in some applications for safety reason. And I don't know the numbers yet, but from the feeling definitely the polycarbonate was the strongest. And now it's time to check the layer adhesion. These test objects are printed in vertical position, and here the smallest cross-section area is also 4 by 4 millimeters. What is not visible on the footage is that I'm using my own weight to break these test specimens because I was expecting smaller loads, but I think I should move to the chain hoist here too. After breaking, again I can see that white area on ABS, and only one test specimen didn't broke on the smaller cross-section area. Shear stress. These test specimens have a diameter of 5 millimeters, and it will be a double-sided shear stress. And they all broke correctly on those two cross-section areas, this meaning 3 pieces. It was a little bit hard to find all 3 pieces from polycarbonate because it just exploded, broke very suddenly. And again I can see these white areas on ABS. This is 3-point bending test. Distance between supports is 50 millimeters, and I want to record the load at 2 millimeter deformation and the maximum load. And after the test, only PLA and polycarbonate broke completely. The PETG, ABS and ASA just deformed. And again, watch this white area on ABS. In this torque or twist test, I have these test specimens with 6 millimeters in diameter. This side goes into this torque meter, and the other side goes into the vise. And I will rotate it, and I will follow the torque in Newton meters. And I want to record the torque at a 90-degree angle rotation and the maximal torque. PLA 1.9. 2.0 is the peak. PETG 1.4. 1.6 was the peak. ABS 1.5. 1.5 was the peak. ASA 1.4. 1.4 the peak. PC 2.2. 2.2 was the peak. For the filling, I wouldn't say there is any significant difference in between them, and they all failed approximately after a little bit more than half rotation. With this Izod impact tester, I want to see how much energy is required to break these notch test specimens. I'm following here the ISO 180 standard. 0 position, PLA, PETG, ABS, ASA, PolyCarbonate. And after this test I can see that ABS and ASA didn't break completely, but let's analyze the numbers and the images. This is the scale and this is the 0 position. This is after breaking the PLA test specimen, and very similar is the PETG. And ABS was the strongest in this test, but also ASA was very strong too. And the most brittle is the PC, the polycarbonate. And this may be the main reason why you don't want to print, let's say, warranty CD printed parts from polycarbonate, but from ABS as suggested by designers. And if I enter all the lines and measure the distances from the 0 position, with this equation I can calculate the breaking energy in joules, but if I divide it with the cross-section area, which is 8 by 4 millimeters on that notch cross-section, in that case I can calculate in kilojoules per square meters, because this is the specification given on the Polymaker's website. My next experiment is the temperature test, and I have these test specimens. They are not perfect yet. I try to go closer to the ISO 75 standard. Anyway, I placed here the M10 nuts on it, and I want to record the temperature when it starts with deformation. Oops, this one is bigger. Sensor of this thermometer. I'm starting with heating. Now, theoretically, according to the ISO 75, I should record the temperature where the deformation is bigger than 0.32 millimeters. And these are not standard bars, my test specimens, so I'm a little bit far from this ISO 75. It's 120 degrees Celsius inside, and all test specimens lay down to this silicone pad. And I can stop the experiment and analyze the results. Every filament is very soft for the touch. If I can hold it with my hand, not yet. Something what I expected, the PLA started with the deformation first, then PETG. I wasn't sure about ASA and ABS, but I know that polycarbonate will be the last which will deform in this test. And now let's measure the hardness with this short D durometer, and I will measure it perpendicular to the layers. PLA 70.5, 70, 70.5. PETG 71, 71, 70.5. ABS 71, 71.5, 71.5. ASA 73, 73, 72. Polycarbonate 76.5, 78, 77. So from these 5, the hardest is the polycarbonate. If this would be a metal, then I know that it would be the most wear resistant, but I'm not sure what is the case with the plastic. Now I'm preparing my first step of the creep test. I have these C test specimens. Distance between these two surfaces is 12 millimeters. The creeping is the deformation of the material during the constant load. If you want to learn more about this test, then I will place a link to that video down in the description. The load will be 1.25 kg weight. And the last one will be improvised because I have only 4 pieces of these types. And now I will measure the start values, but to more precise measuring, I will lock the position with this element here.
14.74, 16.36, 15.79, 15.88, polycarbonate 15.13. And this is after day 1, I already measured them. Day 2, day 3, day 4, day 5. And now 1 hour inside the heated enclosure, but actually inside the oven, and it will be approximately 47 degrees Celsius inside. The sensor. And my enclosure I left on my workplace, so it will be heated in this oven, and I will follow the temperatures on this thermometer because it is not very accurate. This is the current temperature inside the oven, and this is the alarm temperature, so if it reaches this temperature I will open the door, so I want to keep it between 45 and 50 degrees Celsius. 1 hour passed and I didn't have to open not even once the door, because from 46 it went up slowly to 48. And this is the position after heated enclosure, and I can see a significant deformations on PLA as I expected. And I always like to record the removing of the load. And after 10 minutes, so the best is the polycarbonate, ABS, ASA very similar. I can see some deformations minimal on PETG now, but very permanent big deformation on PLA. And later I will analyze this data in Excel. And now I am preparing the second type of the creep test. And in a vase I will hold only these two nuts. And now I will tie these bolts using this torque wrench, and tomorrow I will check with this angle meter if I can tie it even more using the same torque. All test specimens are ready, and tomorrow I will see by applying the same torque if I can move these bolts, and I will measure it with this angle meter. This is PLA, and now let's see with applying the same torque if I can move these bolts anymore. (22 and 28), and I will calculate with the average. PETG, day 1 ABS, ASA, polycarbonate, day 2 PLA, PETG, ABS, ASA, polycarbonate. And this is end of day 2. PLA, PETG, ABS, ASA, polycarbonate. End of day 3. PLA, PETG, ABS, ASA, polycarbonate. And this is the state after day 4, absolutely no movement of the polycarbonate. PLA, PETG, ABS, ASA, polycarbonate. And this is the state after day 5, and now it goes to the heated enclosure for 1 hour. PLA, PETG, ABS, ASA, polycarbonate. And these are final results, day 5 after heated enclosure. And it's time to analyze the data, and I will start with the creep test. And this is the raw data from that C bending creep test. And this is what I usually presented in earlier videos, but basically with the creeping, what is important is the deformation between 2 days. So that's why I prepared this data, and this will be presented in the graph. And 0 means it doesn't have any creeping. There are some negative values, but that may be the inaccuracy of the measuring. And the screw test, basically it already shows this difference between these 2 days. I added some new data, for example in megapascals, the tensile test, because this data you can see in the specifications table, but this is easier for understand. If I tell you that the test specimen has the smallest cross-section area 4 by 4 millimeters and it breaks on 100 kilograms, then you can imagine the strength of that object. Okay, let's analyze the graphs. The creep test. So as I mentioned, the 0 is the best, and this is the C bending creep test, and this is that rotation screw test. And the all test specimens except the PLA on the day 2 they almost stopped the creeping. So this is very small difference. And the PLA stopped with the creeping, let's say on third day almost. But you can see after the heated enclosure, well, the PETG couldn't handle so good that temperature, but especially the PLA. So definitely 47 degrees Celsius is too much for the PLA if it has some constant load on it. And very similar results is with that screw test. So the PLA showed the most creeping. The best was the polycarbonate in this test. Then let's say the tensile test, the layer adhesion test, and shear stress. And you can see the scale is equal, 220 kilogram max. And the polycarbonate was the strongest in tensile test, and very impressive. Look at these values. So layer adhesion test, even the ABS and ASA 40 something kilograms, that's also very good, but this was really impressive, 81 kilograms on layer adhesion on polycarbonate. The shear stress is very similar, but again the polycarbonate showed the best properties here. Bending test and torque test, I noticed in earlier videos too that they are very similar. Maybe I will place in the future next to each other these two graphs. And yes, the PLA and polycarbonate was the strongest in these tests, but don't forget the PLA only on room temperature. If it would be some constant load, especially a little bit higher temperature, in that case this would be completely different. And impact test, so energy of the braking, and ABS was the best, but ASA is also very strong here. PLAs was very similar like earlier other PLAs. I was a little bit disappointed on PETG in this test, and well, polycarbonate, it is very brittle, so definitely it cannot handle impacts. It may break very suddenly. And last, something what I expected, so the PLA was the weakest, polycarbonate was the best here. ABS, ASA very similar. I was expecting a little bit better, higher temperature here, but don't forget this is not standard testing yet. I try to make this closer to the ISO 75 standard, but that's the question for the future videos. And latest is the hardness, very similar, but of course again here the polycarbonate was the hardest here. If this would be a metal, then I would say that it is the most wear resistant, but I'm not sure is that the case with the plastic too. And if somebody wants to download this table, it is available on mytechfun.com website. The link is down in the description.
A lot of broken plastic here again. I know it's a very long video, but trust me, the work was very long too. But you always have the contents down in the description, so you can jump to any part you would like to see. And don't forget, probably you don't even notice that there are no ads during the video. About the materials. Let's see if you want to print without enclosure, then print with PLA. The only reason you would like to choose PETG over PLA is if you need a little bit more temperature resistance and less creeping, because PLA deforms under constant load even on a room temperature after a longer period of time. So if you want to print inside an enclosure, well, definitely polycarbonate is a great material. From two reasons it is not my favorite. one that I noticed later that it gets some warpings. It is hardest for printing between these three. Definitely using a brim would help in this case, but I didn't use it. And the second reason is that it is very brittle. So if you expect your 3D printed part that it will get some impact, well, polycarbonate may break very suddenly, so that's why I don't recommend it to print, let's say, some plastic parts on some DIY 3D printer. For that, ABS and ASA would be much better, and the ABS is actually the best between these five on that impact test. Why would you like to use the ASA? Well, let's say if you want to print something which will be outside on direct effect of the sun, in that case ASA is better choice because it is UV resistant. I hope I could cover everything. If I skip something, you know, drop me a line in the comment section. And in a few weeks the Polymaker line will be tested and presented in this video. Until that, thank you for watching and happy printing.